So hi everybody, I'm Russell. I am from Oakland. Don't hold it against me. But I came out to this meetup because I was really excited to meet people working in tech in New Orleans. We are thinking about moving out here. And I thought, what better way for you to learn a little bit about me than by me giving a talk about something super nerdy that I love. So let's talk about me just for a second. I am a software engineer at a company called DataStax. It's a company that spends a lot of money selling Apache Cassandra, which is a distributed database, along with integrations with a bunch of other things like Lucene, which is in Solar, and Apache Spark. And just to get into it, Spark is a distributed analytics platform. So basically we've got that problem. Everyone talks about buzzwords. We've got big data, we've got lots of data, we've got lots of computers, and we want to make that data processed on all those computers at the same time because maybe it doesn't fit on just one computer, or maybe it exceeds RAM on one computer, or maybe it's some fault tolerance guarantees that we have to be worried about, and we can't have our job failing just because half of our machines go down, or maybe a whole data center goes down, or something like that. So to start with, people started doing distributed analytics with MapReduce. You guys probably heard of Apache Hadoop. This is from the original Google paper on Hadoop. It's really boring. But the important things to see about this is that we end up with these files that are ostensibly in something called HDFS, which is a distributed file system. They go onto a bunch of different machines. Each of those workers is a different machine. They have something done to them, get written out to a different file. Then those secondary files get read again. And something else gets done to them, and then we write to another file system. Now this is bad for a bunch of reasons. One of the main ones is that we got this HDFS thing at both ends of here. And this is like one phase. So one MapReduce requires I/O at both ends. I need to read everything and I need to write everything. So if I want to do two phases of MapReduce, like I want to MapReduce and then I want to MapReduce again, like I've got two different functions I want to apply to my data, I just had to do I/O on everything that I was working on twice. So this is a little scary. And one of the other problems with this is it's a pretty rigid model, right? I have to write a mapping function and I have to write a reducing function. So everything I'm doing to my data, I have to express in this really kind of complicated paradigm. Like, a lot of people don't come into computer science, especially out of most traditional programs, like knowing about mappers and reducers and like those kinds of functional programming concepts. And if you wrote MapReduce code for Hadoop, it would look like this. And obviously this is like garbage. This is a ton of boilerplate and ridiculous stuff. Don't worry about it. But the important thing is that the only things that MapReduce knows about your code is that it knows you've got a function that is called map and takes keys and values. And you've got a function that's called reduce and takes keys and some kind of iterable number of things that just got mapped. So there's no insight that MapReduce has into what you're actually doing. It doesn't know what's happening inside of those two functions. It just knows that you'll give me a chunk of data. I'm going to apply this function over and over and over and over again. I'm going to do some kind of shuffle, moving files around so that the keys are together. And then I'm going to run a different function. And that's all it knows. So this was pretty great at the time because there was really no other simple way of saying, I've got a ton of data and I want to do stuff to it. It was just impossible. I mean, you ended up writing things like on the Sun Grid engine and stuff like that, where you're writing custom formats and file transfers to say I need the data from here to go to there, and all kinds of weird stuff. So that's bad. So let's redo the architecture so it looks a little cleaner and we have an easier way of expressing ideas about how we want to actually manipulate all of this data at once. So Spark looks a little different. It's got this client which has a Spark context in it, which knows about a couple different machines. And when you want to do work, it builds up a directed acyclic graph, a DAG, of a bunch of pretty common collection operations that you're probably familiar with from functional programming. So I'm going to take elements, I'm going to map them, I'm going to change them from one thing to another, I might filter some out, I can do a group by, I can do some more maps, all these kinds of pretty common collection operations. So instead of writing a mapping function and a reducing function, no matter what I'm doing, I can actually just write pretty much normal collection operations, as if I was working on a giant collection. And what Spark would do is it takes this DAG and it converts it into little blocks of metadata that get sent out to all of these remote machines. And these remote machines all say, okay, I got this piece of metadata that tells me how I accomplished this particular piece of work for this part of the DAG, and then they each do their little piece, and then the results stay in memory on that machine, and send back a reference to the Spark context that says this is where the completed work is in memory. So if you want to pick up on this, if you have another step that needs to work on the same thing, we don't have to actually read it off the disk again. It's already in memory. We can just point to that node again and say, oh, you're supposed to pick up the work that you just finished. It's already in RAM, just keep it there, and apply another function to it. So instead of having to go to disk over and over again, we have this really nice kind of very flexible architecture where we can chain almost anything together over and over and over again and never touch disk unless we really need to spill out of memory. So this is pretty great. This also lets us do things where we actually can say like, well, when this piece of work is done, we know where it is, so we can do local operations on it. So if we're moving things around, we know where it is, and the Spark code itself can say, oh, I know these things are co-located, so we don't have to send anything over the network, we don't have to read anything, we don't have to write anything. So that's basically how that looks. And this is that same code, this is just a word count, but written in the RDD API for Spark. So this probably looks a lot more familiar. I mean, all we're doing is we add 1 to each tuple that's coming through, and then we reduce the ones with the same word and count them up. So we add, if we have a bunch of words, each one gets a 1 next to it. If you have the same word, the ones get added together, and that's it. So we have this really nice, pretty clear API as opposed to how MapReduce was working, where we had to write these pretty big boilerplate filled functions, and we end up writing a lot of code to do a very tiny amount of work. Here we have to just write a tiny amount of code, and we can do a lot of cool distributed programming. And the reason that we can do this is that RDD that I'm talking about, this is the underlying class inside of Spark. It's a resilient distributed data set. And what it is just a class. It's basically, you can think of it as a collection of some type. And it's made up of partitions, and each of those partitions is some amount of independent data that can be worked on independently. And when we do these operations, it simply takes one partition at a time and does the map operation on it, as if it's an iterator. It goes through and does all the work on it. There's a little more work when we have to shuffle things together, like when we have to do that reduce by key, but basically this is what's happening, is we have this giant collection where we have all these different big pieces of data that can be worked on different machines independently. So like I was saying, basically, every application of a function is going to be like taking our partition, which is just an iterator of that type, and applying maybe a function that changes t to s, and then we end up with a partition that's made up of s. And that's really all that's happening. So the API has got a bunch of pretty common functions: map, flat map, filter, group by, reduce. There's a whole long list of all kinds of other things you can do. And the thing to know is that this is all lazy, right? Because it's all just building up this directed acyclic graph. Every time you apply another function, you're just adding another node on it. This is another function to apply. And then it's also got a bunch of things called actions, where that will terminate the DAG. This is something to do that says we're no longer going to do any more processing, so the output of this can't be an iterator. It needs to just be something else, like we need to be writing a file, summing it all together and getting a single count, or just doing an operation on every one of those fully processed records. So I just kind of wanted to go quickly through that because this is no longer the easiest way to use Spark. This is kind of the building bones of how everything else is put together. And the reason that this is no longer the prime API for Spark is that Spark has a similar problem that MapReduce had, in that we can't look into this function. The function that's being applied in your map, in your reduce, is a generic function. So Spark can't actually look inside of it and say, oh, this function, it would make a lot more sense if you applied your filter before your map. Because if you did your filter before your map, there'd be less records to apply your map function on. But because those are just generic lambdas, there's no way of Spark knowing that that's a safe swap. So that's a big problem with this RDD, is that we don't actually know what's happening inside of our operations. And the second is that we don't really have a solid type understanding here. We've got this RDD maybe of type K, but maybe K can be reused when we make T. Is K a part of T? Is K unrelated to T? Is there some way we could use the memory we'd already allocated for K to make a new T? Like, there's all these kinds of things that if we had more information about what these underlying types were, we would be able to do really cool things. So, to solve that, so in this world, if you want to do optimization, you have to know and you have to actually move operations around. If you know the filter should happen before the map, you have to move the filter before the map. So, enter the data frame dataset API. So it has two big things that are huge pros that I think a lot of people think are cons. One is that it has a very fixed schema. That means that when you are working with a data set, it's a collection, but it's a collection built up of very specific types. You have basically, integers, big-ints, strings, all the kind of stuff you normally find in a database. And it also has a very limited API. So the reason that these two are actually huge pros and not cons is basically what happens if you have them. So if you have fixed schemas, we can do a lot of awesome stuff. One of the cool things is if we know exactly how the data is laid out, we can work on it without serializing it into Java objects. Because if we know that every row is going to be an integer, and then a string, and then a date field, why even make it into a Java object to do an operation on it? We know how to work on bytes when they are integers. We know how to work on bytes when they're actually representing a date. We know how to do all this stuff, and we can do it all at a native level. We can actually do it with compiler optimization. We can do all kinds of cool stuff, and we can do that automatically for an end user who's using the system. So in Java, we end up having to do all this kind of serialization because all the time we're taking these things out of memory and making Java objects from them and calling methods on them. Well, if we have these tungsten rows, if we have these internal representations where we know how they're laid out in binary, we can actually just look at the byte buffers themselves and call functions on them. So there's a huge savings here because there's no serialization needed, and there's also a lot of efficiency because the methods we're using are way closer to the method. So this is really cool because all of this can happen without the user actually understanding how it's happening, because all of this can basically just be generated for them. So the limited API part is what lets us take another really cool step here. So here's just a little Scala example. I really love Scala, so I've got almost all Scala examples when I talk about stuff. Where we just take a bunch of words and we're going to do a group count, or we're going to do a word count. And you'll notice here we're using this group by with a little funky value there. That's a column identifier shortcut in Spark. And basically, this is making a data frame. And you'll notice the data frame instantly knows exactly what its schema is. It knows that the output of this operation is going to be a string, and it's going to be a count. And when I just do a little count show, I actually print that out. And you can see that it actually did do a word count. And the reason that this limited API, that this group by, is better than doing just a group by key, doing something with a random function in it, is that under the hood, this is happening. So this is pretty awesome, and I'm going to go through it pretty slowly. So up at the top, all I typed in was group by value count. Under the hood, Spark looked at that and first built up a query tree. So like it's an SQL engine, like some kind of database engine. It looks at this, and it says, this is actually built up with these specific nodes, these operations, these logical operations. We're logically going to be aggregating based on the value, and then we're logically going to be pulling this from this local source of information, which is that create command I have with the sequence. So then it has a stage of optimization where it takes that very abstract, just basically what the query I typed in, and it transforms it by expanding wildcards, by looking up references. So if I was referring to a table in a different database or a file on a disk, it would actually resolve, look up that file name, make sure that it existed and all that. And then we get to the second step where now we know the exact output of what's going to happen. We know that we're going to do an aggregation, we're going to do a local relation. there's an optimization stage, and at that point, there is nothing happening in this particular one, but we could do things like reordering our filters, we could take joins and push down predicates through our joins, so that we're basically most efficiently executing the intent of our first query. But that's completely gone now from what's actually going to happen. And then finally, we get to do another set of optimizations where we have this built-in set of different kind of transformations that looks at this logical plan and says, what is the most efficient way to do this? So one of the cool things that you'll see here is it's doing a hash aggregate here. So it basically looked at the data and looked at the thing that I requested it to do and said, the smartest thing to do for this is not to actually do a distributed shuffle. It's not smart to take all of this information, write it to disk, send it to other machines. Instead, the smartest thing to do, because this is a really small thing, is to build a hash map. Just build a hash map up and aggregate that way. So it did that all automatically, though. I didn't have to tell it that that was the smartest thing to do. It just automatically said, oh, that's what you should be doing in this case, because I'm looking at your data, I'm looking at the structure of what you're requesting to have done, and this is the best way to do it. So this is the actual series of this will happen, and this will happen, and this will happen. Well, everything above here is just a logical expression of these are the things I want to have happen. So this is very high level down to what actually will get done. And if you're wondering what happened to RDDs and all this, well, that actually is all going to be done with RDDs. So it builds up this whole thing, figures out how it's going to do it, and builds up a string of these RDDs together, so it's using that framework to actually do all the work. And another cool thing is that since all of those operations are really well defined, you can see they all have very specific names in the plan, it can actually do code generation and write low-level code, compile it, and then run it within all of these RDDs. So instead of actually doing those actions on Java objects, it's actually running all kinds of low-level code on the byte buffers, doing manipulations at the byte level to get all of this done. So that's really why I think that having schema and having this limited API are really awesome. And another cool thing is that when you do things this way, if you have this kind of optimization that happens for anyone using this dataset library, there are all sorts of other libraries you can then build on top of it that get all of these optimizations for free. So anytime this optimizer is improved, all of the libraries which use this API are also improved. Because all of them, they can all take advantage of the same things. So just some examples of that is there's an API called GraphVariants, which is a library that helps you do graph kind of work. So if you're interested in taking your data and representing it as a bunch of nodes and edges, and you want to do traversals or look for patterns like highly connected components and things like that, you have that. There's an ML package, which has a whole bunch of neural net stuff and more basic stuff like linear regressions and Bayesian things, just all built in that uses this under the hood, so you can end up doing distributed machine learning. And then one of the coolest aspects for me, since I work a lot with Apache Cassandra, it's one of the main things in my job, is that it allows us to take data from a whole bunch of other sources, and we can connect it into this system in a way that's really, really easy. So if you want to read data out of the Cassandra database and out of MySQL or Oracle or something like that, and combine them, you can do that in this system, because in this system, they're both the same. It sees them as this same underlying format that it knows how to deal with. So you can actually combine and save out to all of these systems after doing these huge bulk manipulations. So that's like one of the biggest things that my job is basically about is I work on the connector here that connects this to the rest of the Spark ecosystem. So we'll have users who are like, well, I've got 5 terabytes of data in my cluster, and I need to change something around. I have to manipulate some column. And that's obviously non-trivial, right? I have to basically rewrite terabytes and terabytes of data. So they'll use something like Spark here, because they can suck all the data out, change it into this format where their DBAs and the people on that end can actually just write SQL, write some kind of really easy transformation, and get the data to write back out to this and use their giant clusters and all that kind of stuff. So this is also super useful because this dataset API is available in a bunch of awesome languages. You can write it in Python, you can write it in R, Scala, Java. And what's been really important for me lately is SQL. Because we've got a lot of customers, we've got a lot of people and users who are not familiar with Scala, don't want to learn Scala, think Scala is really terrible, and they're wrong, but I want them to be happy too, so SQL is available and they can just write SQL queries, because a lot of them have 20 or so years of writing SQL queries, and they know how to do that. And now they can write an SQL query and end up doing a huge amount of distributed work. So it's this really kind of cool platform and balance there. So that's all I really had prepared to give us an overview, because I know that's a lot of things to cover. And I was hoping that you guys would have a bunch of questions to further drill down on some of this. But if you didn't, I could keep talking about some other things that are built into the platform. Yeah?
Atlas, if you're mentioning, kind of reminds me of that SQL Server or MySQL plan.
Exactly.
So is it just suggesting what to do, or is it actually making the modifications for you?
It's actually making those modifications for you. So what you write is just like in SQL, right? You write a declaration of how you want the results to look, and then it decides how to actually do it.
Is it creating the equivalent? Look at SQL explains here, or Postgres explains, you tell me I'm missing an index, or how do we structure it? Is that what you would expect to see out of that? Is something to tell you the equivalent of that in?
Yeah, so I can show, I have that explain up.
Yeah,
So like here, this is where you'd be looking, you'd be like, so they're obviously not the same kind of things, because like you don't have indexes and things like this, but you'll see like, oh, I'm doing the full shuffle when I do this. All my data is going everywhere. Or, oh, that predicate didn't actually get pushed down to the right part of the join, or these joins are happening in the wrong order. I should really reorder my joins. You know.
so you do use this in the way like the DDAs
Yeah.
would use SQL, so what's before I'm
Exactly. Yeah. Because there's obviously still a lot of work to go into like this kind of stuff. I mean, they just in 2.2, which was just released this month, they just did the first batch of join reordering. Because before that, joins were just whatever order you put them in your query or built in your query through the API. That's the order they would happen. And obviously, that's terrible for a lot of things. And you know, there's similar things like with matrix multiplication and stuff like that, where just doing it in the order that someone gives it to you is probably not the best idea. Yeah.
How much does the size of the data change?
Currently, a lot. The biggest operations in most distributed analytics is the shuffle. It's this idea of, I've got data on different machines, but I can't actually get an answer unless they're on the same machine. So deciding where to do those shuffles, where to do those joins, is really, it's a big part of this. It's like, yeah. And then there's also locality considerations. So something that I didn't talk about too much is that a lot of this all has baked into it ideas of like, this is where the data will be after you do this step. So internally, it can look at it and say, okay, after I've done this operation, I've already organized all of my data where all of the keys are in the same place. You know, all of the, if I'm grouping on Word, I know all of the entries for a single word are on a single machine. So if I'm doing another operation that requires all of the words to be on the same machine, I should order that preemptively closer, because I know that I won't have to move data then in between. So there's stuff about avoiding shuffles, taking advantage of that kind of stuff, and then, yeah.
So we did pull up. Again, I'm brand new to this part.
No, that's fine.
I'm going to be into it in about 2 weeks. But
Cool.
so even going further back, did you say that data ends up partitioned on distinct machines? A notion of shuffle is how using the group by word. I mean, right off the bat, you have no idea where the words are. How mechanically, when in the process,
How does it
go?
so
How does the magic happen so that we know where the words are?
how does
So I can
yeah, so how does the locality magic happen? So this is basically up to the people who are writing the sources. So is anyone here familiar with like Parquet files or Avro? So there's like a bunch of different ways of like laying out your data. There's certain file formats that'll just be like, this file format is set up so that all the values of a certain column are going to be in this file, and all the values of another column are in this file, or something like that. So it can actually ask the source that it's reading the data from, how is it partitioned? How is it set up? And in some cases, it just doesn't know. And if it doesn't know, then it has to shuffle. Then if there's no information or it's not in the right order, you have to shuffle. That's kind of the way it is. Yeah.
How much information about algebraic properties is it? So if you have something that's commutative, does it take advantage of that? How do you explain to the system that it is commutative?
So in data sets, that's one of the things about the limited API, is that the moment you go outside to do your own function, like your own UDF or UDA or something like that, then it doesn't know. But within it, within this system, so there's a bunch of aggregations and things like that, then it does know. So it doesn't have any magic to like look into other stuff, but within its known capabilities, it knows like this is
It
commutative.
still passes functions, right? So
Yeah.
it knows about math. You can pass it an arbitrary function.
But when you do that, you're basically outside of the system.
I see.
Once if you do a generic map, you're on your own.
So if you did a, like, are there operations that would do, instead of like a left fold or a right fold,
Mhm.
they'll do like a tree fold
Yeah.
that assumes that it's monoid and build it up that way?
It's got a lot of those kind of rules built in. So basically the whole rule system is a series of partial functions which takes these trees and it's like, if I have nodes in this particular setup, I can reorder them and make a new tree. So it just keeps applying rules over and over and over until it can't apply rules anymore, and then that's what you get at this point. And then it does the same thing again for this transition, where it's like I've got all these physical rules where it's like, this is where it'll be like, I know how the partitioning works, so I'm going to change this around. Or I know that this data source is actually able to handle those predicates at it. So like this is, you're talking to SQL Server here, and you're asking me, when is this column greater than 5? Well, I know that SQL Server has already got an index on that column, so I'll just have SQL Server do that part for me, rather than pulling all the data in and then doing the filter myself. So stuff like that.
Is every step in the HDFS, or is it only some of them? I missed part of the beginning.
Oh, sorry. Yeah, so in this, unlike in MapReduce, we're never writing to HDFS. We only will write to local disks if we're spilling to memory, or if we have to do a shuffle. On shuffles, we have to, the shuffle algorithm that it uses is a sort merge, which means it's going to write records to a bunch of little files, and it has to write into files because it doesn't know how big they'll be, so it doesn't want to explode memory when it's trying to figure out where everything's going to be. But yeah, so we don't write to HDFS at all, but you can attach
shuffles
that.
in the physical plan?
Huh?
You can see the shuffles in the physical plan, or what do you
Yeah,
see?
so this is a shuffle right here, this exchange. This is technically a hash exchange, so it's probably going to, instead of actually doing a shuffle, it'll broadcast. It'll make the one side, because it thinks one side is really small, into a hash map, broadcast that, and then just look up keys out of the hash map. Because at a certain size, it doesn't make sense to shuffle all the data versus all of the data. You just take the smaller part of the data and you put it on every other machine, and then you just look it up. So it's got a whole bunch of weird tricks like that and stuff that it does.
Can you possibly compare this with things?
Yeah.
The other alternatives?
So
Or,
So I can start with Flink. So Flink is a combination batch and streaming platform, which has a lot of these ideas in it too. A lot of this movement in the Spark product is actually moving to copy a lot of stuff that Flink was basically built from day one with. Flink was started out with like, we will have set schema, we will have set API, because then we know we can do all of this awesome stuff. It doesn't happen to be as popular a project right now. This tends to be a lot more popular, because there's also a streaming module for this. So you can actually do streaming on this engine, and one of their big pushes lately is that this dataset API is becoming the streaming API as well. It's something called structured streaming. So you end up writing the exact same query. You started with like streaming source, and you end it with streaming write, and you just started a streaming application. So it's very similar to the way Flink is doing things. A little more popular right now, and I don't know what else.
like optimizations? Like
Yeah.
the opti store,
Yeah, so that's, I think you might have missed this. So this is where I was talking about, this tungsten representation. They're able to do everything on unserialized bytes, so you can move everything off heap. You don't have any Java objects. You're just basically saying, I'm moving this map to here, and here's your pointers in memory to where everything actually is. You know how to work with it, and all that kind of stuff. So compared to store So the streaming inside of this, which is different than in Flink and in Storm, is currently a micro-batch streaming. So unlike tuple-based streaming, so tuple-based streaming, we have like a single record comes in, we do work on that record as fast as we can, and then we get that record out. So one record at a time. So that is really low latency, because a record comes in and a record goes out as quickly as possible. Then with this, we're doing micro-batches, where we're collecting up some amount of records, then we're processing that whole bunch at a time. And then at the end of the day, we finish all of them at once, which means that the latency of that record, the first one that came in, is only as good as the last. So it has to wait for the last one to be done and arrive and be done before the first one is actually done being processed. So it's technically, philosophically, it should be a higher latency process, but higher throughput. While per tuple, like in Storm or Flink, should be lower latency or faster throughput. But again, it comes down to all the other optimizations and things that are happening that it may or may not matter. And one of the things that they're working on in Spark is they're working on building a similar per tuple based execution based on their structured streaming as well. So that'll probably come out real soon. Probably too.
The asynchronous barrier snapshotting, like
so they do. So since it's per microbatch, they snapshot on a microbatch. You can basically checkpoint each microbatch as it's coming through and say, like, these are the parameters used to generate the incoming data for this microbatch. So you end up with the exactly once processing guarantee, right? Because every time you're guaranteed that each piece of data will go through the full system at least one time, because you're checkpointing when it goes in and you checkpoint when it's done. And it only does anything when it's at the end. So
how's the experience working with this? Can you like Repple build it up? Do small parts of it before running the whole thing?
oh man, maybe I should just have the REPL up, which I'm sure I do. It did not like me moving between Wi-Fi. Let's see if it's even still running.
Are you on the Wi-Fi here?
No, I think it was not happy that I changed IP addresses or resolution or something. Yeah, it was not happy with that. But that's cool. I can just, you know what, I'll just start up a new REPL. So you can run everything. If you love Scala or SQL, it comes with a REPL for both and for Python. So PySpark, Spark SQL, and Spark Shell. Spark Shell is just the Scala REPL, but it's been enhanced so that it can handle the fact that it has to serialize every single thing that it makes out to a bunch of other machines. Yeah, I want to do that. There we go. So yeah, so like I was saying, you can just build it up. You can like make a data set, and then you can, I don't know, you can do all sorts of things. You can join it with itself. You're gonna let me do a Cartesian join right now? I just forget the actual syntax of this. I think I have to pass in a condition, which should be something like, I have to actually like pass in a representation of the join key. Yeah. DS. Should like that. Yeah, I know it's a trivial predicate. Thanks. It did not enjoy that.
Could you do something like count the characters?
Yeah, so I could have done that, but it's actually got a rule on right now to stop me from doing a Cartesian join, because usually Cartesian join is a bad thing to do when you have terabytes of data, so you have to actually set a parameter to let yourself do Cartesian joins.
Do you sample, like, so if you do an exploration like this, you don't want to wait for your Cartesian join to happen across the whole
Yep.
data set? Can you do this for 50 of them?
So yeah, there's limits. You can do limits that'll get pushed through and things like that. And you can actually do the sample, which comes built in, where I can just say, like, I only want half of the data or something. And that just builds a node that I can do other things off of. So that should give me half of the words. but I think it does it on a per partition basis, so it can do that right. I only have one partition.
So when you're exploring and you're trying to do, trying to look at the plans for different queries, do you have to do it against a real data set to make sure that it's going to, because if you do it on a small thing like this, you can do that in memory.
Yeah. You can hook it up to your live data if you want. I think a lot of people do. I mean, a lot of people. I saw that in your meetups that you have a notebook one, a few. So a lot of people hook this up to Zeppelin or Jupyter. There's also Spark Notebooks, and the company that is behind the Apache Spark project called Databricks has their own. So there's a whole bunch of notebook tools that you can also have, and you can always set those up just like attached to your actual running cluster and your data, and actually be working on your real data. Most people, when they're doing testing and things like that, just do a small fake set that they're making sure their things all work on, because there's really nothing about the plan that it builds that is not inherently scalable, right? Everything that it's making for you is broken into pieces and could always be broken into more pieces. So that's one of the key design things.
So you can tell that it's going to do a shuffle even on something smaller.
It might not give us that. It might not tell us the exact shuffles that it will do, because some of those are size-based. Like it has estimates on how big the size of the thing will be after that. So for that, you'd have to actually look. Yeah, sorry, I'm not a great live demoer.
I got a question.
Yeah, sure.
If you wanted to start right after a hello world, a small, simple application, for example, what would be something you suggest for someone?
I think the basics are usually people do a word count, and then people like to do distributed calculating of pi. There's a bunch of these examples that are already built into the Spark project, so you can actually just load them up and look how they wrote them out. Some other good things. I mean, the thing is, usually our users of this are people who already have this problem. They're already stuck. They already have too much data somewhere, and they need to move it somewhere else. So they're starting out with mini versions of that. How do I move all my data from a bunch of CSV files into the database? How do I extract my stuff from Oracle and move it to Cassandra and stuff like that? But I don't know. There's a lot of examples out for this. So I would check out the ones bundled with Spark first, because they're all pretty high quality, and they all work on the most recent version of Spark. Yeah.
So assuming I do want to get started with Spark, and I want to do it not on my laptop, but on an actual cluster.
Yeah.
What's the easiest way to do that?
So it actually comes bundled too with AWS scripts. So if you've got AWS keys, you can put those into the script, and it will launch up a cluster for you, and you can do work on it. So that's kind of fun. It also
You forget to shut it down.
yeah, then you forget to shut it down, and you owe $20,000 to Amazon. It's no big deal. That's one of the easiest ways to get started. I think they also have on Elastic MapReduce on AWS can run Spark jobs now. Databricks, the organization that is the commercialization of this project, has all of their stuff is on AWS, and they have free tiers where they'll give you a few nodes to start out with or to work with for a couple hours. That kind of stuff. Yeah?
Have you seen any good use cases for using RDD without the fixed schema in your experience?
So the thing is, this product has changed so fast that a lot of people are on RDDs, and a lot of functionality is not fully baked into the data set model. So this is some inside baseball, but one of the things I complain a lot about to them is so we all live in very close together, so we see each other and complain about stuff. Is that they don't have a good way of expressing some concepts internally to this dataset API. So for example, a construct that I recently wrote is there's no node in that planning process that says I would like to take this set of highly distributed data and pull it out of a database based on what's already there. What's the right word for this? it'd be like a data set join. So like I've got a data set of like 100 million keys, and I've got a data source that is really efficient at pulling those out one at a time, but is not very efficient at getting them in a full scan, because if it was scanning over everything, maybe I've got 2 trillion keys, and it'd be really dumb to scan over 2 trillion keys just to get out 100 million. So that kind of operation I had to build in myself and like add it to this optimizer and this plan. So that's the kind of stuff that sometimes it's lagging a little behind some of these other optimizations or things that you might want to do. And for example, if you have your own libraries where you have your own machine learning stuff or your own business logic that's already done, proven, tested, it might not make sense to rewrite it, and you just want to just hook it right into an RDD, just have it run. Then there's people who've got like Fortran code and stuff that they've got, because there are a lot of scientists are getting into this now. So like some of the folks at CERN, my background is in bioinformatics, so I know a bunch of people who are like, yeah, I've got this Fortran code I'm going to run. So they just take the RDD, and one of the RDD options is to just shell out to a process and pipe things through standard out to that process and take the output back. So there's like, yeah, I'm not going to rewrite my Fortran code in this. Like, I don't have time for that.
How much can you do, like API calls, like web API calls within Spark?
You can do anything. It's
So
really
you have
dangerous.
A function you can just map.
So there's like no security on it. This is something to know in case you're doing something. So like, let's say I'm going to parallelize a collection. Then I'm going to map all of my elements in this collection, and I'm going to map them to system exit,
Oh.
right? So like, that shouldn't be allowed. Exit 1. So that shouldn't be allowed. So that was just the lazy operation. So if I take the results, oops, I just quit out of my program because I just ran quit within my Lambda. And it was like, that's fine, I'm going to do that for you. You'll notice it's a little confused because it's like, wait a minute, my bus is like still trying to run, but I'm also trying to get results, and I don't know what's going on. But yeah, so there's nothing stopping you from doing anything, which is both bad and good.
And almost you don't even know what machine it's going to be running from.
You don't. There's a bunch of UIs and stuff. If I start this up again, I can show that off real fast. Yeah. I know we're already bound
Is there
to
an
everything.
FTP data source?
An FTP data source? I think there is through HDFS, through the HDFS APIs, through the Hadoop APIs, because all the Hadoop APIs for reading files are valid here. I mean, there's definitely S3, which is what most people do, because if you've got so much big files, you probably have them in S3 anyway, because you've got these giant cold things that no one's ever looking at. So the UI is pretty cool. So like if I make a data set, I can just run something I've already typed in so I don't break everything. And we do some cool work. And later on your boss is like, so why didn't that finish on time? Actually, we are not there. Started up on 41, didn't we? That autocorrect. No? 4040? Yeah, there we are. So we've got this, I guess this is probably really hard to see too, so let's blow that up. We got this nice UI which shows us like how many pieces it got broke up into on each step as it was doing work. And then there's nice tab over here which is absorbing all of those complicated data frame things, and it's letting us track exactly how much time they took, what it did, and we've got all these cool statistics, how big things were, did it actually distribute nicely, how many rows were processed, all this kind of fun stuff. You can see how it says host stage code gen everywhere. That's that where I talked about how it's actually writing code for the byte buffers underneath. That's what's happening in there. And yeah, so there's actually a lot of stuff there to see. figure out what's going on.
You mentioned it holds all, it's holding all the data in memory across all these nodes.
If it can.
If it gets it, right. So, what's the behavior if a node fails?
So you're able to specify what level of retention you want. So either you can mark your data set as being required to be in memory on more than one machine, so that will end up duplicating these buffers onto multiple machines. Requires a bit of cost. If there's none, if it's lost all replicas, if there's no longer an instance, everything it's got has a hierarchy, a dependency chain. So it can decide how far back do I have to go to actually get that particular partition recalculated, because it actually has this this graph, right, that says like you take this and then you do that to it, and then maybe you mix it with other pieces, and then eventually you do this to it. So it will look back and see what work needs to be done to minimally recreate that piece. And that comes into some of the finer tuning of this, is where you would say, well, after I do a lot of expensive operations, I might cache my data in memory. I might make a copy, or I might copy it to HDFS or something like that, and make sure that after I've done something that maybe takes 2 days, I write that out so that next time I just read it back up. So I don't have to go back through the entire tree if something breaks on the next stage.
But something like a built-in and sort of recalculate, look back, that's all built
That's all
into
built
the
in.
platform. That's
Yeah. Built in, if you lose something, it just looks at the graph and it says, how do I get back to this point? Then redoes everything that it needs to. Which, if there's a shuffle beforehand, means it has to redo the whole shuffle. So that's the kind of place where you're like, pause. I need to take stock of where I am, so in case something breaks, I can keep going.
But again, if you want to do that, that's explicit gestures.
That's explicit.
Your own, that's
Mhm.
not-
Yeah. The setting how many copies you want when it's actually working, that's also explicit. You say, like, I want memory and disk. I want there to be a memory copy and a disk copy. I want memory and disk too. I want every machine to have, or 2 machines to have a memory and disk copy of every chunk of thing that gets computed.
And you normally decide those parameters just based on experience.
Yep.
You run it, it breaks too much, and you say, I need more backup.
Unfortunately, yeah. So Spark is unfortunately also a pretty young project. It's 4 years old, maybe. It's got a lot of hype behind it and a lot of people using it. So a lot of the worst stuff has already been cleared out, but it's definitely still got a lot of kind of scary corners.
I mean, it sounds like a better model than Hadoop.
It's way better than Hadoop. For someone who I also worked on Hadoop before I worked on Spark.
Isn't Hadoop like someone's weekend project? You read the MapReduce paper and
Hadoop's got a lot of heart inside of it. It's rough. So like Hadoop had a bunch of its own solutions to this. I don't know if anyone's interested in hearing about that. So like there's things like Hive and Pig. Everyone knows about Pig, right? This is functional programming meetup. Pig was this horrible Lisp-based, it was a Lisp-based engine to try to make MapReduce easier. So you could write a Lisp comprehension to do your work instead of writing a MapReduce job. But it basically had tons of these things that were made, and Hadoop has a bunch of main distributors and companies backing it. Each of them sells their own custom versions, so none of it all works together. So you get to basically pick which vendor you want and hope that all of their stuff will satisfy everything that you're looking for. I don't know. It's not as much fun.